Alexandros Vanakaras.
Yeah, I will introduce myself. Okay, and I'm going to present the work mainly done in the University of Patras with Professor Fotinos and two very active postdocs, Droulias, Sotiris, and Stavros Peroukidis. I'm going to talk about biaxial nematics. This is an old story. Actually, it was predicted in 70 years ago from Fraser in the improving the Meyer-Schaupe theory.
Not yet 70 years, but in the 70s.
In 70, yeah, okay. And later, Straley constructed the molecular model for this phase transition, actually a board-like particle with the dimensions shown here. Okay, it works. And he proved that when the dimensions of the particle meet certain criteria, then these particles may produce stable biaxial nematic phases. And this criterion is the self-duality. So the dimensions of the particles should be such in order the particle to be neither prolate nor oblate. So he was able to predict all this phase diagram in terms of temperature and the width of the particle just using a simple shape parameter of the particle. So depending on the sign of this parameter, we could have the phase transition from the isotropic to uniaxial, plate-like, disc-like uniaxial, and then to biaxial. When the shape parameter this is 0, we can have a direct transition from the isotropic to the biaxial state, and when nu is greater than 0, then we have rod-like nematic to the biaxial nematic. So this is a huge success of this very simple theory. On the other hand, experimentally, we know that we can have much more complex situations. For instance, in the lyotropic systems studied by you and Schaupe, in a very narrow range of concentrations of this mixture, of this ternary mixture, we can have phase transitions that involve disc-like to biaxial phase, reentrant disc-like, and isotropic again, or even more complex phase sequences. Of course, here, the entities, the micelles that formed, may change shape, so this is the reason we can have all this this very spectacular phase sequence with temperature in this lyotropic system. Later, we had biaxial nematics in polymeric systems like this in '87, or in oligomeric systems, tetrapods, which have been shown that they exhibit biaxial nematic phases. Probably the most famous compound that exhibits thermotropic biaxial nematic phases then these bent core mesogens reported first by Samulski that they exhibit stable biaxial nematic phases. All the systems I described before are quite complex. The polymers, there are too many parameters in order that are involved to the molecular biaxiality. By far the most simplest system that exhibits stable biaxial phase up to now is these geothite particles reported a few years ago by Van der Poel and Lecker-Kerker's group, and this system, this colloidal system, when the dimensions of the particle is close to the length to the width and the width to the thickness are more or less equal, then increasing the density, the system starts from the isotropic phase, condenses in a nematic biaxial phase, and afterwards appear some symmetric A biaxial and the coexistence between crystalline and symmetric biaxial phases. The biaxiality of these symmetric phases is under some question, even in these works. On the other hand, this system shows very interesting reentrant nematic phases upon the application of external aligning fields. So we have a very simple system. The interactions between these colloids are short range steric interactions. So we have a very nice model to check theory and simulations. What is very surprising is that there are no simulations at these very simple models, the Borg-like particles, up to now. And this is quite strange. Actually, there are simulations of particles of this symmetry, biaxial ellipsoids by Mike Allen, and they show, indeed, that when the geometry of the anisotropy of the particles meets certain criteria, they have this dual shape, it can give biaxial phase. But there is a drawback here. The ellipsoids do not allow for symmetric phases. Actually, the competing phases of these biaxial phases are not present here. This is by construction of this mod of the ellipsoids, as was pointed out by Frenkel in '87. So the other attention was by our group. We thought that, okay, if we have Borg-like particles that they give uniaxial phases, only uniaxial phases, and mix them, then this length polydispersity can destroy the symmetricity of the phase sequence, and a stable nematic phase appears at a certain composition. But in this model again, the particles were restricted to be perfectly aligned. Okay, so we don't have an isotropic phase here. Okay, here we don't have the symmetric phases, the ordered phases. Here we don't have the disordered phase. So in order to fill this gap, we simulated these Borg-like molecules, which actually are Borg-like cuboids with decorated with half cylinders around them. And the nice feature of this system is that if both the thickness and the width go to 1, become equal, and equal to 1, then we have this system transforms to a spherocylinder, a well-studied system. And for this system, we assume only excluded volume interactions, hard body interactions, and we are going to see the phase diagram of this using Monte Carlo simulations. Note here that in the highest packing of this system, the packing fraction tends to unity. Actually, they can fill almost perfectly the space. So I will present some results for these three systems, the system A, B, C. All of them have the same length to width, equal to 3, and what it changes is the thickness of these particles. Okay, and the shape parameter introduced by Straley is almost 0 for this system, for the system B, and positive for the system C. C should be there, and negative here. So if we put these numbers on the Straley's line in the width to the L diagram, then all of them are very close to the range where biaxial phases are expected. So let me start with the system C. The system C, which have this positive shape parameter, condenses from the isotropic phase at a packing fraction almost 0.45 to a rod-like nematic. And with a first-order transition, it goes to a smectic A phase. It's a very typical situation of rod-like particles. So here what we have the order parameter, the main order parameter of the z-axis of this particle. The biaxiality is 0 actually everywhere. And the order parameter of the x-axis of the particle, which is in the very ordered state, it goes almost to minus 0.5. That it tells us that it is oriented perpendicular to the main director. The biaxiality order parameters, they introduced by Roberto in the previous talk, so I will not talk about them very much. So I will switch now to the system A. Here, the situation is very different. We start at a packing fraction 0.30% with a disk-like nematic of this system. So that means the x-axis of the particle orients along the director. So we have a discotic, and at increasing the pressure, it transforms to a calamitic smectic A. So we have a discotic phase, and this transforms to a smectic A calamitic-like. This, to the best of my knowledge, this phase sequence has not been reported neither to from simulations, neither from experiments. And of course, in lyotropic systems, we have this kind of transitions. The biaxiality here, again, is the systems are not biaxial. In the system B now, we have clearly the appearance of a biaxial nematic phase, of a proper biaxial nematic phase. And this biaxial phase transforms again, increasing the density or the pressure into a smectic A phase, a uniaxial, again, calamitic-like smectic A phase. So if we follow here the order parameter, let's say, of the x molecular axis, this is positive. That means that the director is defined by this. And when it passes to the biaxial nematic where the z molecular, the long molecular axis becomes more oriented, then we have this change of sign. The order parameter along the z-axis becomes positive and the other negative. Here is the biaxiality of this phase. These snapshots are not look very nice. Now, in order to analyze these phases, we used the pair correlations which depend on both position and orientations. And we define them, we take this R as the relative distance between two molecules, and omega describes the relative orientation of this. If we expand this function in terms of these rotational functions, which are related to the Wigner matrices, then we can construct the rotational invariant radial pair correlation functions, which is this one, which is the usual radial pair correlation function, which is the orientations have been averaged, and this correlation functions that describe the relative orientations of the molecules as well. So here we plot this function. Actually, this function tells us how the orientations change, the orientational correlations change with distance. Actually, how the second Legendre polynomial. Here we can see that in the smectic phase we have a quite high order parameter, and going to at the isotropic phase, these correlations decay to 0 in the isotropic phase quite fast. The same is true for this correlation. Again, that confirms that all these phases are unambiguously, we have long-range orientational order. And we have identified it with this way, the axis with the highest molecular alignment. Now, if we go to the biaxial correlation, the radial correlation function that describes the biaxial correlations of this particle, we can see that for the system A, they decay quite fast to 0. For the system A, where the shape parameter is close to 0, this is the system with the dual shape. The isotropic phase goes to 0. In the nematic biaxial phase, the disk-like biaxial phase, we have these correlations does not disappear at long distances and increase with pressure. But when we go to the calamitic biaxial phase, these biaxial correlations decay and finally, in the smectic phase, disappear. So the smectic phase is macroscopically uniaxial. The same picture have for the other system. Again, here we see that the biaxial correlations, even in the isotropic phase or in the uniaxial nematic, are longer, have longer range than these correlations in the smectic phase. This, I think, we should give an explanation why these correlations, these biaxial correlations in the smectic phase decay so faster. So this is a picture of the smectic phase, and this is the way the molecules are arranged within the layer. We can see here a tendency of the particles to stack face to face, and these chains actually are randomly oriented, and this destroys the biaxiality within the layers. Actually, this is because the anisotropy of the two-dimensional, the cross-section anisotropy of these particles is not enough to produce a long-range order in two dimensions. And this actually is confirmed with simulations by Bates and Frenkel of 2D systems, where they have shown that in order to have a nematic ordering here, the cross-section should be more than 8. In our case, this cross-section is about 3. So everything is consistent with what we know from previous simulations. Now, if we calculate the density profile around a single molecule, then we can see that there is, in the wall range of pressure, persistent structures which extend different depending on which direction we look at the particles. And this patterns actually agrees quite well with the XRD patterns calculated in the papers of the heart of the colloids, of the real colloids. And actually, if we measure the distances here, we see that even these distances agree quite well. So what we did, we measure in a simple way the correlation length along the several directions of this particle. And we constructed with these correlation lengths, the extent of these structures, a shape parameter which refers actually not to a single molecule, but rather to the correlated domain of the molecules. If we plot this supramolecular, let's say, shape parameter, we see that this parameter changes sign close to this nematic biaxial to the nematic disk-like biaxial to the calamitic biaxial nematic. So it tells us that the supramolecular correlations around these hard particles change shape with density and pressure, and actually they change this shape and in different directions of the particle. We have analyzed this correlations in a more proper way. So we have calculated this density profile. From this density profile, we calculate a distribution-like function in the two-dimensional, and from these functions, which actually is a measure of the structure of the system around the molecule in 2 dimensions, calculated the second moments of these distributions here. We were able to estimate in a way the length, the correlation length of these domains, the size of these domains. And actually, in order to have a measure, an independent measure, we have scaled these dimensions with an ideal, the corresponding ideal lengths where no correlations exist at all, no positional correlations. So I have plotted all these lengths, the extent, the size, the shape of this supramolecular structure in this plot. We see that along the main changes, what changes actually with the pressure is the size of this correlation length along the x axis of the molecule. And if we calculate the volume of this correlation length and compare with the corresponding volume of this correlation length of hard sphere systems, then we see that this correlation volume in these anisotropic materials are at least 2 times higher than the correlation volume in hard sphere systems. Note here that at these packing fractions where we have all these nematic and smectic phases in the hard board-like particles, the hard sphere system is still in the isotropic phase. It's quite far from the crystallization packing fraction, which is almost 0.5. So, the whole story of this system is here. We have done several simulations, and we were able to construct it to trace the phase boundaries of this actually cuboid, of this board-like particle. What I have plotted here. Here is the width of the particle, and here is the length. So, depending on the width and on the length, we can have this kind of phase sequences, isotropic to rod-like nematic and to smectic. When the thickness, the width of the particle becomes bigger in comparison with here, we have isotropic to disk-like nematic and after to columnar. There are certain combinations of L and W where we have a direct transition from the isotropic to the smectic phase. And what is quite interesting is this area around the Straley's line. Here we have phase sequences which include the biaxial nematic phase that transforms to a smectic phase. There is a small, narrow region here where the system condenses from the isotropic phase to a disk-like nematic and then to a SMEC decay phase. And this completes the full story of this model. Clearly here, we have the critical geometry of this molecule. Well, when L is 9 and W is 3, then we have a critical point, and small deviation from this point can change the phase diagram, the phase sequence of this system dramatically, and can lead to totally different phase diagram. Let's show this a bit closer. When we have particles, biaxial particles with length, let's say, greater than 9, and let's start varying the width of this particle. When the width is small, then we have, okay, isotropic nematic to smectic. There is a range of widths which is well located here. For these widths, we have isotropic to nematic biaxial and then to SMEC decay phase transition, and a wide area where we have isotropic, disk-like nematic, and then columnar phase. The situation is different when the length of the particles is lower than 9. Then we have a window from the isotropic phase condenses directly to a SMEC decay phase, and for small W, small widths, we have isotropic nematic, rod-like nematic, and SMEC, and for large widths, we have isotropic nematic, discotic, and columnar phase transitions. Note here that for a system with L equal to 9, to this critical length, then we have a direct transition from the isotropic phase to the SMEC, and these W's here, these windows, actually merge to a single point here. In all these systems, there is always a narrow range where we have a transition from isotropic to a discotic phase, and then to a SMEC A phase. This is the first time, this is unpublished results. This is a full phase diagram of this very simple model. I can make some first conclusions here that these phases we have observed have very clear local structures, and the macroscopic density drives the growth of the size of these correlated domains anisotropically in a different rate, different directions, and influence as well the inter-supramolecular correlations, and this can lead to nematic phase transitions. And okay, we hope that all these results will help to a better understanding both to the liquid-liquid transitions and of the nematic phase. And we think that this nearly exact computational experiments will be a very good guide for experiments towards the design of desired functionalities, as well to theory for testing and improving analytical molecular theories and models using this very simple interaction potential. Let me now, what time should I finish?
Well, it breaks to 22.
Huh?
Well, you have at least 10 minutes.
Oh, okay. So we have this the bent core nematics. The picture for this bent core nematics is more or less similar with the picture we expect for the board-like nematics of the biaxial phase, I mean. But for these systems, there are questions. Are they spontaneously biaxial or field-induced? Or are these the usual molecular biaxials, or the cybotactic clusters, nematic clusters, characterize these nematic phases? And the same compound that has been reported as biaxial, it has been reported from John Goodby's group that under the polarization optical microscopy, the system appears to form spontaneously chiral domains. This non-chiral system. Okay, all these are very interesting questions. And in order to check whether this picture of clustered phases, we have constructed a very simple model in order to describe this phenomenologically, this cluster nematic. So take this nematic of n molecules between these two plates. Here the long axis of the bent molecules are along this, and these domains are clusters, biaxial clusters, where in their interior there is a biaxial order, but in this picture they are uncorrelated. Starting with this picture and going to the molecular level, we can construct molecular tensors, either vector or second rank tensors, and from them we can construct the cluster tensors that describe the average, let's say, polarity or orientation of these clusters. Now, these order parameters, the local biaxiality and the macroscopic biaxiality, is some proper order parameters of this system, and having them, we can construct a Landau-Dezen free energy, which in the case we have clusters that are biaxial, will be a power series of the cluster biaxiality, the local order parameter, and of the macroscopic biaxiality, plus this very simple coupling terms between these two order parameters. In the case we consider that the local clusters are polar as well, then we have, together with the macroscopic biaxiality, we have a local polarity, an order parameter which describes this polarity, and the macroscopic polarity. In the same fashion, we can construct the Landau free energy for the system, which has two more couplings between the polar and the biaxial order parameter, and we allow for the coupling with an external electric or magnetic or aligning field in general. So with this simple picture, we can see, we can observe, we can predict phase transitions from molecular nematics, where these clusters are very small, actually, are zero. So in this case, you have a uniaxial nematic. We have uniaxial phases, but with clusters developed, which are biaxial, but this cluster, the directions, the biaxiality of these clusters are not, does not point in the same direction, so overall the phase is not biaxial. And another nematic, which is a proper biaxial, where all the clusters have the same direction. And the same picture we can have for polar clusters, where these are uncorrelated, then can be ordered but antiparallel, so overall the phase here is not polar, but it is biaxial due to the local polarity. And of course the low temperature phase is the phase where it's macroscopically polar and biaxial. So a typical phase diagram from this Landau expansion starts with a uniaxial phase where we don't have any clusters. We have the transition phase, a first order transition in a nematic uniaxial phase with polar clusters, but uniaxial overall, to a biaxial nematic phase with polar clusters again, but overall non-polar, and okay, the low temperature phase, we don't care about this for the moment. And we see here that the response of these phases to the application of external fields depends crucially on the existence of clusters or no. So we can see here that even a small field tends to 0 here can produce huge biaxial correlations or biaxial order within our sample, even this sample is overall uniaxial. Now, we want to check this theory, this clustered theory, with again using some simulations in order to measure this local structure. To do this, we started with the atomistic detail of these oxadiazoles and model the bent core molecule, assuming that this molecule consists of from a rigid core and from some edge chains that are able to rotate. Okay. So we put several molecules of this kind in a simulation box, and we were able to see a phase transition from the isotropic to nematic phase and then to a smectic phase. But for this system, where the molecular conformations of this molecule have a preference to be the chains to be out of the plane of the bent core, we see that the same system can be end up with this twisted state. So we start with a system which is with a molecule which is achiral, and this system can go either to a macroscopically uniaxial nematic or to a macroscopically twisted mesophase, nematic mesophase. Here, this helical superstructure has confirmed for several thousand of molecules. Again, the same system at the same temperature condenses either to a uniaxial phase or to a twisted nematic phase. So, what does this tell to us? It tells that the free energy difference between these two states is quite small, actually. But since we never observed a transition once we have a nematic phase from one nematic phase to the other, it tells us that the barrier between these two relatively close minima should be quite high. So this system can easily be trapped in one of these states. I will not bother you too much with the positional correlations of this molecule, but I would like to stress here. Here we have a two-dimensional profile of the polar correlations of this molecule. Okay, in the nematic phase. In both nematic phases, in the twisted and the uniaxial, we take the same picture. We see that the polar correlations extend along the x molecular axis in longer distances than in the side by side. So when it is side by side, the polarity dies quite after small distances. Okay, the picture with correlations along the XZ molecular axis. The positional correlations are, it's what we see here. It indicates clearly that in the nematic phase, we are in the nematic phase. We have short-range correlations, smectic-like short-range correlations. And from this plot, we can see that the polarity, the XX correlation, changes sign from layer to layer. So we start with something positive and moving along the Z-axis, it changes sign here and becomes negative, and in the next layer it becomes positive. So clearly both nematic phases composes from smectic-like clusters which are antiferroelectrically aligned. The polar correlations in the uniaxial phase along in the YZ molecular plane again confirm this change of the polarity along the layers, but in the twisted nematic phase we have this kind of rotation in right or in left-handed phases. We see that the positional correlations are not anymore symmetric. So this suggests clearly, this rotation, that in the twisted nematic phase, these cybotactic clusters are of smectic, anticlinic, and polar, and in an antiferroelectric arrangement. So this is actually the correlation lengths we measure are in quite good agreement with the experimental results from XRD calculations. And actually they does not change too much with temperature. Again, in order to see if this picture, the cluster picture, is in accordance with the phenomenological observation, we have done the following experiments. In our nematics, we have applied aligning fields along that tends to align the X molecular axis either in that way, in this quadratic way, either polarly. And we measure these electrobiaxial and electropolar coefficients. Polarity of the system change with the electric field, and here is how the biaxiality of the system changes with the application of the electric field. And the results we get are consistent with the phenomenological picture that our phase is in the nematic phase with in a uniaxial nematic phase with polar clusters. And instead of conclusions in this section, I would like to give these pictures from a very recent publication, this impressive picture. They are cryo-TEM images of the nematic phase of bent core molecules. And here, Zackley and others were able to observe in the nematic phase the existence of these cybotactic clusters optically now, not through X-rays or other experiments. And the dimensions of these clusters actually in the high temperature nematic phase are of order of a few molecular lengths. in accordance with the sizes we predicted with our molecular simulations. And probably this is the reason why in these bent core systems we need relatively low magnetic fields in order to induce phase transitions. A common calamitic requires huge fields in order to shift the phase transition either for a milli percentance of Kelvin. Here, with moderate fields, the phase transition, the pneumatic to the isotropic phase transition can be shifted for several degrees. And this is consistent with the cluster picture of this bent core pneumatics. So, I will end with this. So we have biaxial phases from board-like and from these molecules, bent cores. Here is a picture of the local structure. Look this movie here. So these molecules can rotate about themselves, about their long axis, simultaneously, without any overlap. Okay? Here, for the board-like particles, in order to do this, they can't do this actually, because they have all these strong overlaps, you can see here. So, the molecular theorists that wish to study, to see all this local order in more detail, to study this synchronized rotations of these bent core systems, should go beyond the Onsager approximation. So it is not enough, this entropy of a single particle orientation. We need to add contributions from entropy, entropy contributions because of the orientational and positional correlations of pairs or triplets of molecules. And this should be should have a very big contribution for this system. Okay. And I finish with this, and you are all invited to the next European Liquid Crystal Conference, which will be held in September in Rhodos. It is still summer in September in Rhodos. And for more information, okay, you can visit the website of the conference. Thank you for your attention.
I think since we're eating into the tea break, we probably ought to leave questions to informal ones during the break. So thank you very much again.